Hello everyone, I am Samuel. Today in this video, I am going to discuss previous year questions from NET December 2011, particular from this topic solid state physics. Okay, so I will discuss the solutions in detail and if needed, then I will mention also the tricks. Okay, so the first question is the potential of a diatomic molecule as a function of the distance r between the atoms is given by V of r, that is equals to minus a by r to the power 6 plus b by r to the power 12. Okay, the value of the potential at equilibrium separation between the atom is, so which option is correct? Okay, you have four options given, then you have to find the correct one. So potential is given here, V of r, that is equals to minus a divided by r to the power 6 plus b by r to the power 12. And firstly, you have to find the bond length, that is the equilibrium separation between the atoms. Okay, so firstly you have to find the equilibrium separation between the atoms. So what is the method? So given here V of r, that is equals to minus this one. Okay, so for determining equilibrium separation between atom or bond length, that is equals to r naught, del V over del r, you have to partially differentiate potential with respect to r, as the potential is function of r. Okay, so and equate it with 0. Okay, so further calculation you will get this answer, r naught whole to the power 6, that is equals to 2b by a. So if the question is for bond length or equilibrium separation, find equilibrium separation, then you have to find only the r naught. Okay, so r naught will be 2b by a whole to the power 1 by 6. Okay, now the question is the value of the potential at equilibrium separation between the atom. So the value of the potential at equilibrium separation between the atom is, so you have to put this r naught value, okay, here in this for equation. Okay, so V of r at r naught, that is equals to minus a square by 4b. You will get this by calculating these stubs. Okay, so option D is correct one. Okay, you can find this option D is the correct answer. Okay, now second question is if the number density of a free electron gas in 3 dimensions is increased 8 times, its Fermi temperature will increased by a factor of 4, decrease by a factor of 4, increase by a factor of 8, decrease by a factor of 8. Okay, so here given number density and number density increased by 8 times. Okay, so what will be the Fermi temperature? For solving this question, you need to know the formula of Fermi energy. Okay, so what is the formula of Fermi energy, and in 3 dimension? Okay, so you need to know the formula in 3 dimension. Okay, the Fermi energy formula, you can get the Fermi energy formula in 1 dimension, 2 dimension, as well as 3 dimension. So you need to know the formula in 3 dimension also. Okay, so the Fermi energy formula in 3 dimension. So I will suggest you to memorize this kf value only. Okay, kf value. So kf value is 3n by v pi square whole to the power 1 by v. 1 by 3. Okay, so if you know the kf value, that is the Fermi wave vector for 3 dimension. Okay, so n by v, that is the number density. So okay, you can write it also as 3n pi square. Okay, so EF, that is equals to h cross square kf square divided by twice m, that is equals to h cross square by twice m into 3n by v pi square whole to the power 2 by 3. So you can write this as h cross square by twice m 3n pi square whole to the power 2 by 3. So this is the undisturbed. Okay, so this is the undisturbed EF, and now we have to increase the number density with a factor of 8. Okay, so you have to put only the n value, that is equals to 8n. Okay, so you can easily find this EF prime, that is equals to 4EF. Okay, so and also you know that EF, that is equals to KBTF, and KB is the Boltzmann constant, and Boltzmann constant is constant for all systems. So KBTF prime, that is equals to, here you can write 4 KBTF. So KB cancel out, TF prime, that is equals to TF. So TF prime will increase 4 times of the temperature TF. Okay, so the answer is here increase by a factor of 4. Okay, next question is, the excitations of a three-dimensional solid are bosonic in nature with frequency omega, and wave number k are related by delta proportional to k square. This is the dispersion relation. You can write it as omega proportional to k square in the large wavelength limit. Okay, if the chemical potential is 0, the behavior of the specific heat of the system at low temperature is proportional to, here 4 options given. Here you have to find the correct one. Okay, so the dispersion relation is here omega proportional to k square. Now you can find the energy value from this dispersion relation, and you can easily find the CV value. So but that is the that calculation is quite large, quite time taking. Okay, so I will come here with a trick, very easy trick for this question. So if omega proportional to k to the power s, if omega proportional to k to the power s, you can write it as omega. Okay, so omega proportional to k to the power s, then you can write Cv proportional to t to the power ds, d by s. The d is the dimension and s is the this value. Okay, so Cv that proportional to t to the power 3 by 2. So you can find also the energy value, you can find also the number density. Okay, number density with temperature variation. Okay, so this question is basically from the Bose-Einstein condensation. So Bose-Einstein condensation is a very important and very interesting topic for physics student basically. I will make a video on Bose-Einstein condensation later. Okay, so what we learned from this topic basically from this question paper. So for bond length calculation, you have to partially differentiate the potential with respect to R and put the R value as R naught. That R naught is the bond length. Okay, so second, you have to memorize this Kf formula in 3D, that is 3n pi square whole to the power 1 by 3, and energy formula that is equals to h cross square by kf square. This is the typical basic energy formula, and ef that is equals to kbtf. And omega, if omega is proportional to k to the power s, then Cb proportional to t to the power d by s.